Great. Thanks so much. Excited to be here. Helion's a new DSL. It's lower level than PyTorch, but higher level than Triton. So the obvious question is sort of why a new DSL? And you could view this from two directions, sort of from the PyTorch side. Working on torch compile, one thing we often hear from users is they want explicit control over a specific fusion that happens. And that's something that PyTorch doesn't provide, but Helion provides that while staying very close to the level of abstraction of PyTorch. And so you can sort of think of Helion as PyTorch with tiles. And then from the Triton side, there's a lot of areas in Triton which are sort of a little bit tedious, a little bit too low level for some people. But also, a big thing that we're seeing and a big trend is hardware heterogeneity. A lot of companies are now using multiple vendors for GPUs. A lot of companies are announcing their own custom hardware and deploying that hardware to production. And one thing we see is that even if a Triton kernel can run on lots of different types of hardware, it isn't performance portable on different hardware. So we have lots of kernels that are optimized for one specific model, and even if a new GPU model comes out, or if you switch to a different vendor, the performance isn't good, and you need to make a lot of rewrites to your kernel. And having sort of a higher level language that can provide performance portability was a big motivation. And so a big thing that defines the design of Helion is its autotuner. And really, the autotuner is the sort of the silver bullet that allows you to use a much higher level language, but then delegate the search over lots of different ways of implementing and optimizing your kernel to the autotuner, so you can get a high level language with the performance that you'd normally see in a much lower level language. And so the design of Helion takes inspiration from lots of things like Halide, which have a very simple sort of semantics language and then a scheduling language which you can automatically tune. And sort of Helion does the same thing, where one Helion kernel mapped to thousands of different Triton kernels, and we have an automated search to search over different ways of implementing your kernel and get the best performance out of it. So you could sort of view this as you're handing a lot of the development process that would be manual in a low-level language to the machine and letting the machine do the search for the optimized implementation. So here's an example of what a matrix multiply looks like in Helion. So the Helion kernel has two main parts. So you have this outer part, which is just standard PyTorch code, and you use this to allocate your outputs and do some shape computations. And then you have this inner part, and this inner part gets mapped to a single Triton kernel. And so this outer hl.tile loop becomes the grid of the kernel, and the inner tile loop you iterate over. And this and within this loop, you can use standard PyTorch operations. So if you know PyTorch, you already know a lot of different parts of Helion. And so the most important construct in the Helion language is this hl.tile construct. This hl.tile construct takes a shape that can be multi-dimensional, and it subdivides this iteration space into tiles. And it intentionally doesn't specify how the space is subdivided. So basically, we leave it up to the autotuner to subdivide the iteration space. And the autotuner can autotune not only the tile sizes, but it also can change iteration orders. It can do flattening. It can turn your 2D iteration space into a 1D iteration space. It can do swizzling and so on. This gives the autotuner a lot of flexibility to explore different ways of implementing your program. So next I want to talk about the configuration space, and this configuration space sort of give you a much better sense of what Helion is doing, especially if you're familiar with sort of the equivalent Triton. So the first piece of the autotuning space is indexing choices. So in Triton, there's a lot of different ways to do indexing. You can do pointer indexing, you can do block pointer indexing, you can do tensor descriptor indexing. What we found is that often the best indexing strategy depends on the sizes. So often we see that for small sizes, pointer indexing is faster. For large sizes, tensor descriptor indexing is faster. And it can be pretty tedious to rewrite your code to switch between these different ways of indexing. And so in Helion, we just have sort of PyTorch-style indexing, where you index your tensor with a subscript operator, but you index it with these tile objects. So you're basically loading a tile at a time. And the configuration which the autotuner searches can switch between these different indexing strategies automatically. The next feature is that we autotune over is the block sizes. And block sizes are incredibly important for the performance of a kernel. And in Helion, block sizes are implicit. So you just write hl.tile, and then implicitly is defining some number of block sizes. While in Triton, there's just a lot of boilerplate to deal with block sizes. So I sort of highlighted sort of all the places the block size sort of gets threaded through the launcher to compute the grids. Grid computations are automatic in Helion. And this makes it much easier to search over different block sizes. And by making this block size definition automatic, it also allows us to do stuff like loop flattening. So if you set config.flatten loops equals true, we take this two-dimensional block size iteration space, we turn it into a single one-dimensional block size iteration space, which can be faster, especially for memory-bound kernels. And this would be a substantial rewrite to a Triton program, but it's just a single config flag change to a Helion program. The next one I'm going to talk about is reduction rolling. So suppose you're taking the sum over rows of a two-dimensional tensor. There's really two ways to do this in Helion. In Triton, you can have you can load the entire row into a single tile and then reduce there. The problem there is that if your row is very big, if it doesn't fit in a single SM, then this code will either start register spilling, or it just will refuse to run because it gets too large. And so the second way of doing it is writing a loop with an accumulator. And Helion sort of automates this transformation and can auto-tune over both ways of doing these types of reductions. Next is different PID types. So you can use the launch grid to define your program IDs, or what you can have is what's often called persistent kernels, where you launch a fixed number of programs, one per SM, and then have those programs iterate over a virtual program ID. And this allows you to pipeline across programs and can sometimes be faster. And we automate the search over different types of program ID mappings. Next up, I'm going to talk about LTIL grouping and loop reordering. So because we're defining the tiled space automatically, we can automate different reorderings of the iteration space. So you can, if you have loops, you can reorder the loops, and then you can also introduce sub-blocking for better cache efficiency, which can be done automatically in Helion. There's lots of other things where Triton exposes tunable parameters, and Helion just sort of passes these through to Triton. But it's automatically able to search over the space of these parameters, where users who are writing Triton programs by hand will often neglect to even try setting some of these parameters. And so this allows sort of the tunable knobs that are in Triton to get exposed to the Helion autotuner. Then finally, masking is automatic in Helion. Masking can be tricky to get right, and by understanding the tile, having these sort of tile objects where tiles understand that they're sort of the last tile and they need to mask off some elements, we can automatically insert masking, and then we have optimization passes to remove the masking if you have sizes which don't need it. So next up, I want to talk about the autotuner. So Helion autotuning currently takes about 20 minutes to search 12,000 configurations. And today we have a few relatively simple auto-tuning techniques. So we have pattern search, which is the default one, and then differential evolution. In the future, we're really excited about LLM-guided searches. We think that especially for such a large iteration space, AI should be able to automate a lot of the search and do a much more intelligent job than these more classical auto-tuning algorithms. And so this is an exciting area of future work. But first, let me explain sort of how the basic autotuner works in Helion. So this is the pattern search autotuner. And what we do is we start with an initial population of just randomly selected configs. So we generate a bunch of random configs. We benchmark them all. And we select the top 5 best configurations from this random search. We then take each of these configurations and hill climb to a local minimum. So we look at all neighbors, and we repeatedly go to the next best neighbor until we stop getting improvements. And then finally, we select the fastest from among all these different searches. And empirically, this works pretty well. We found that the search space for these programs is pretty regular, and we've had a lot of good luck in searching it. But especially for more complex kernels, we can imagine that more sophisticated techniques would be required. So how do you deploy a Helion autotune program? Because the autotuner in Helion is much more expensive than the autotuner in Torch Compile or Triton. And so you really want to do it ahead of time. You should basically take your program, run the autotuner in a development or staging environment, and then deploy the results of the autotuner. So the most basic way to do this is when the autotuner is done, it prints out a configuration. Here's an example of what a configuration looks like for a map mall. And you can just copy and paste this configuration into your code and deploy it that way. And this works great for a single configuration where you want to do the same config for every shape. But you also might have a case where the best config depends on sizes. So you might have like a small size and a large size. You can run the autotuner twice. You can save those configurations. And then in the Helion kernel decorator, you can specify multiple configurations. So here's an example of that. And this basically does the exact same thing that the Triton autotuner does, is it just tries the list, every configuration you provide in the list, and it picks the fastest one for every unique shape. Then, if you want to get even more advanced, you can do manual configuration routing. So you can ahead of time compile your small config and your large config. Then you can write sort of a wrapper function here, like routed my kernel, which basically says, okay, if the numl is small, then call the one, otherwise call the other one. So now I'm going to talk about some performance results. I'll go through 3 different case studies and then provide some sort of more overview of the performance on some different hardwares. So the first case study is a performance of attention. So here we have attention implemented in Helion, where we have 3 different variants of attention. Or 3 different variants. They're the same code. So the first variant is Helion attention with stock Triton. The second variant is Helion attention using the Facebook experimental branch of Triton, where we've implemented better warp specialization algorithms. And finally, we have the same thing, but we've added advanced compiler configurations, which is a low-level way to tune PTX-AS. And then we compare that to PyTorch Eager, Flex Attention, and then the tutorial version of Triton, tutorial version of Attention from the Triton repo. And we also compare to Gluon and cuDNN. And so what we can see here is that Helion, with the improved warp specialization in our branch, is able to roughly match the performance of Gluon, but both of those are still lagging a little bit behind the performance of cuDNN. So next case study is comparison to TileLang. So this is reproducing some of the results from the TileLang paper, where we're looking at a Mamba 2 chunk scan kernel. And we can see that Helion's able to significantly outperform TileLang on all the shapes that they shared in their paper. Then the third case study is comparison to Qt DSL, where we're looking at some Quack kernels. for RMS norm backwards. And what we can see here is that the quack kernels are pretty good for the larger shapes, while we see that torch compile is actually outperforming for the smaller shapes. And the Helion and then sort of equivalent fused Triton code that is pretty close to what Helion is generating are able to give good performance across all different shapes. So taking a step back, so this is now looking at a number of different kernels. And for each of these kernels, we're taking a selection of representative shapes. And then we're taking the geomean speedup over PyTorch eager mode for each of these different shapes. And we can see that in most cases, Helion is either faster than torch compile and handwritten Triton. The handwritten Triton here is mostly taken from the Liger kernel repository. But we basically see that this is really highlighting the power of sort of the autotuner, where even though all three of these solutions are generating Triton code, we can see that there's a lot of room for optimization in Triton code that's used in production, where by autotuning, you can squeeze more performance out of Triton than where people are getting in practice by handwriting kernels. So these are the same results, but now on an AMD MI350X, and we see a similar story here. This sort of shows that as you go to different hardware, you can rerun the autotuner, and you can get optimized performance that works for a wide variety of hardware targets. Helion also works on lots of other hardware. I've shown NVIDIA and AMD, but we've also tested it on Intel XPUs and MTIA. What we found is that because Helion is emitting Triton code as its output, for hardware targets that already support Triton, you can basically get Helion for close to free. However, if a specific hardware target has hardware-specific optimization points, or like hardware-specific flags, you can get better performance out of from Helion by exposing those hardware-specific flags to the Helion autotuner. So for NVIDIA, we expose a lot of warp specialization details to the autotuner. But for different hardware, there's different concepts that require different abstractions. And basically, what the hope is for Helion is that the core language remains the same across every piece of hardware, but you expose different configurations to basically allow the search over how to best optimize something for a specific hardware target to be automated by machines. So basically, machines and in the future AI will be the ones porting kernels to different hardware, not humans. Okay, so I'm going to briefly talk about the internals of how the Helion compiler works. Helion is a Python embedded DSL. So it starts off with a Python AST. We annotate the Python AST with types and metadata, and then we convert this to what we call a device IR. And the device IR has a collection of FX graphs, one FX graph per basic block, connected with control flow operators and phi nodes. And then associated with every node in this graph is an inductor IR. So inductor is the compiler that backs torch compile, and we're basically reusing inductor's compiler to map PyTorch code into Triton code. So this is what allows the vast majority of PyTorch operations to work transparently inside of Helion. We basically have inductor convert them on an op by op basis. So we're not using any of the parts of inductor which operate on the graph, because for Helion you just have one kernel. There is no graph, or there's no graph of kernels. There's a graph of operations. But basically the stuff that does the sort of pointwise and reduction code gen is all reused. And then sort of once we've done all this pre-processing, we bring in the configuration at the end, And the nice thing here is that the configuration is only done only incorporated later on. So basically everything on the left of this diagram is just run once per autotuning, and then everything on the right is repeated for every configuration we're exploring. And this is what's done for everything inside the HL.tile loop. For everything outside the HL.tile loop, that's just standard PyTorch code. So we use basically AST rewriting to replace the loop with a function call in the host output code. And with that, we have a beta out now. We'd love for you to try it out and submit bug reports. And then if you want to connect with us, we have a channel on the GPU Mode Discord. And then we're giving a live webinar and Q&A, which will be in early December. And with that, I'll take some questions.
Yeah, hello. Yeah, so that was a very great talk. So, so you mentioned that you are using Inductor as part of the pipeline for Helion. So do you also see Helion as a torch compile kind of target? Because it seems like it's doing this kind of auto-tuning in a higher level kind of search space, and that seems like a very good fit for torch compile. And so that's what I'm wondering, whether you're planning to integrate Helion as a target instead of Triton for Inductor.
Yeah, that's definitely something we're interested in. I didn't talk about that very much here, but Helion also has a lot better support for templating than Triton does. And because of that sort of improved support for templating, you could imagine a lot of the sort of handwritten kernels that are in Torch compile, like mapmul and attention, could be written in Helion. You could also imagine Torch compile outputting Helion at some point. There's a bit of a circular thing there, because if Helion is using Torch compile and Torch compile is using Helion, then you have sort of a dependency cycle. The other potential roadblock is just the cost of autotuning. So Torch compile will, when Torch compile does autotuning, it'll try 3 configs, while when Helion does autotuning, it'll try 3,000. Which can be much more expensive, but that's something that we'll be looking into in the future.
Yeah, because the things like the using block pointers versus not using block pointers, persistent versus non-persistent, like some parts of that can actually be useful for Torch compile as well, like even in a smaller auto-tuning space.
Yeah, that's definitely true.
Yeah, thank you.
I have a question. The question, or I don't know if it's a suggestion, but basically what I'm thinking is that right now the search space has to be predefined, but there's no concept of the time for auto-tuning or the search. So for example, some like critical applications, like we are trying to use it for robotics, and what happens is that if it triggers like an auto-tuning step or a compilation step, then we would need to have some guarantees on like a solution. It's fine to execute slower, but like it's not fine to not execute.
Yes, so the auto-tuning model for Helion is ahead of time auto-tuning. So no one should be running the Helion autotuner on like a production cluster with hundreds of thousands of GPUs. That doesn't make any sense. What you do is you run the autotuner in a development environment, you take the configuration of the autotuner, and then you deploy that. So Helion kernels, there's a flag called static shapes, which defaults to true. So the default behavior is we will recompile for every shape, but we won't rerun the autotuner. We'll just apply the configuration that's given. And the reason why we do that is we see performance speedups by hard coding shapes in the Triton code. So there you take a performance hit by doing dynamic shapes in Triton. If you set the flag static shapes equals false, then Helion will generate shape agnostic code, which should work for any size. And so if you want to have sort of a no compile environment, you should set static shapes equals false. You can then, even if you want, ahead of time compile the down to Triton, and then ahead of time compile that Triton down to PTX, and just deploy that PTX to get sort of a stable production environment.
Like what we have seen is that you do need access to the shapes. For example, we may have like a range of shapes, but then like the cache which it generates, like the kernel caches, like we cannot have that cache on the robot itself. So we do need auto-tuning, but like having, like the way we do it right now is just to reduce the search space. And like in search, you can also have like anytime search kind of methods to allow for like auto-tuning, but like doing it with some limitations. So that's what we have found. Like if you go for dynamic shapes, then like there's no guarantee of like anything, right? Like you cannot optimize for anything. But if you if you don't go for static shapes, then your just like kernel like doesn't work at all if you have like some change in shapes.
Yeah. So I sort of covered this a little bit in the auto-tuning section, where if you know like, oh, I want my model to work for these 10 shapes, then you can like ahead of time run the auto-tuner for those 10 shapes. Then from that you'll get sort of 10 tuned configurations. You could deploy those 10 tuned configurations to the robot, and then sort of like on the robot you could select between those 10, either with like a handwritten heuristic, or you could write sort of like a little mini auto-tuner which will just try the 10 and then pick from the 10. So you could view that as sort of like a dimensionality reduction for the auto-tuner.
Makes sense. Thanks.
To add to the last question, so my name's Brian Boyer. We work on Triton backends for things that are not GPUs. What kind of information can we give you to reduce the tuning space? Because this is fascinating to us, but we're worried that like, are you just optimizing for GPUs? Like, how would we help you to tune better?
Yeah, so I think that's exposed. This is sort of what I was talking about before about exposing hardware-specific knobs. So like some of the knobs that we expose for GPUs are things like warp specialization, which don't really apply to things like MTAA or most other types of hardware. But those other types of hardware, might have like special hardware for doing device-wide reductions, and that doesn't have a concept that's equivalent in GPUs. And so maybe you need to expose a different set of knobs to the autotuner. And so one thing you could do is you could modify Helion to basically add sort of these extra knobs that are specific to your hardware. Helion also has some language constructs that allow for user-defined knobs. So if there's something that Helion isn't searching over in its autotuner, but you think is a really important choice, you can define sort of a custom user-defined knob, and then the autotuner will search over that. But definitely like that's sort of like the main work of adding new hardware is sort of exposing the right things in the search space to exploit the features of that hardware.
You sort of implied for MTIA that you already do this. Do you do this for MTIA?
The MTIA support is very early, so it runs on MTIA, but we have not done any of the exposing of the knobs work.
Thank you.
So I have a question about how the autotuner works. Does it in any way depend on the Triton autotuner?
It is not using the Triton autotuner at all.
It's a separate process.
It's a separate process. So really, the Triton autotuner, the user supplies a list of configurations. It tries all the configurations to pick the fastest.
Right.
So if you specify 10 configurations, it'll try 10 configurations and stop. The Helion autotuner is much more open-ended. So the search space that Helion creates implicitly will contain an exponential number of configurations. And so the Helion autotuner is basically an open-ended autotuner, where you don't need to specify what to search at all. It'll just sort of explore the space automatically. And because of that, we need more complicated autotuning algorithms, and then also a different framework for doing this search.
Right, so a follow-up question is, so it sounds to me like the Helion autotuner will only work with the Helion kernels. Is it possible to take an existing Triton kernel and use it with the Helion autotuner?
No, you'd have to rewrite it in Helion. Helion does support inline Triton code, so within your Helion program, you can say like hl.inline Triton and just provide a snippet of Triton. So it should be pretty easy to port to Helion because of that. But the Helion autotuner is coupled to the Helion language.
So you're saying if inlining a relatively complex kernel, it should just work with the Helion autotuning?
So if anything you inline won't expose choices. So if you write hl.tile, you've exposed all these choices to the autotuner that it'll search over. While if you just have the entire thing as just one inline Triton blob, well, all the loops and block sizes inside that inline Triton are sort of fixed. So you wanna like at least get the loops into the Helion language, but you can do it in an incremental fashion where you don't need to rewrite everything. You could sort of rewrite it piece by piece.
Okay, thank you.
I think we're out of time.
No.
Sorry to all the question askers that didn't have a chance to ask. I encourage you to grab Jason during the lunch or during the breaks. Let's thank Jason one more time. Thank you very much. Fantastic.